This is SAT Math Manual, Section 18. Section 18 deals with percents, which obviously is a topic that students have plenty of familiarity with by the time they are sophomores, juniors, and seniors. Many students do think that they have a very strong grasp of percents, how to find percents, how to increase things by certain percents, and that's great if you do feel like you have a solid foundation. That will obviously help you here. Having said that, the way that percents are tested on the SAT can be a little bit different from how you have seen them tested in your school classes, in work that you've done prior to the SAT. So we are going to go over some strategies and techniques in this section that are more tailored to the types of percent questions that you will see on the SAT. We are going to start off with a very simple definition of percent. And again, even for students who feel fairly confident about percents, they often don't realize that the word percent can be broken into those two words, per and cent. And remember that per does mean out of or divided by or at a rate of. So what we're going to write here is we're going to write down out of. That's what the per is. And then cent, of course, is the Latin, I believe, root for 100. So the word percent means out of 100. You can also interpret per as for every. So for every 100. And then, of course, there are probably the two most important sort of translations here. Per does also mean, as I mentioned a moment ago, I believe, divided by. So percent means divided by 100. And then finally, we are just going to go ahead and write down a fraction bar with 100 in the denominator. So when we see the word percent, it is often a good idea to understand that the word percent is simply made up of a word that means divided by and a word that means 100. So percent means divided by 100, which means that anytime you see something percent, n% or 10% or 0.7%, you can just think of dividing those letters or numbers before the word percent by 100. Which brings us to percent translation, where we're actually going to apply what we just talked about. So on a lot of percent questions on the SAT, your best bet is going to be to translate. And in this table, in this chart here, we have a bunch of words, obviously in the left-hand column that is labeled words, that can be translated into a symbol or an expression. So we already talked about the word percent, and we said that anytime we see percent, we can think of fraction bar with a denominator of 100. So divided by 100. That's what percent can be translated to. What or what number or a value, those would all translate to an unknown. What or what number, a value means we don't know something, or there's something that we may need to figure out. So that would translate to a variable. Obviously, you can use an n, you could use a p. I'm going to write in parentheses here a variable, just so we don't confuse that x with multiplication. What percent is just a combination of these first two. What percent? What percent means what divided by 100, which means we are doing x over 100. That is how we translate what percent. Is, are, was, were, those are all different ways of indicating that we need an equal sign. In mathematics, is means that two things are equal to each other, two things are equivalent. So is, are, was, were will usually mean we can write an equal sign. Of indicates multiplication. So I'm going to put a little dot there. Again, in parentheses, I'm going to write multiplication just to be clear. We are going to see an example of how this all works in a moment. Increased by or more than, of course, means or translates to a plus sign, and decreased by or less than translates to a minus sign. What we're going to do in example 1 is we are going to translate a worded percent statement, a worded percent calculation according to the table above. I'm going to keep the table visible here, and I'm going to write down at the bottom here. So 54 is just a number. We just write 54. Remember what we said about is an equal sign, so we write 54 is. 75 is a number, but the 75 precedes a percent, so 75% means 75 divided by 100. Of, we said, translates to multiplication, and what number is a variable. So the statement 54 is 75% of one number can simply be translated into 54 equals 75 over 100 times some unknown. We wrote x. That is how we would make a translation out of a percent statement. Now, there is a note over here. We're going to go ahead and actually clean this up and solve it a little bit. There is a note over here that says to put any integers or variables over 1. That may make it a little bit easier to see what your best next steps would be, which would be to apply what you know about multiplying fractions, which is you multiply straight across denominators, straight across the numerators. So we're going to have 54 over 1 still on the left, and then on the right we will have 75x over 100. That's just 75 times x and 100 times 1. And then of course we are in a cross multiplication scenario here. So when we cross multiply, we get 5400 equals 75x, and then of course to isolate the x, we've got to divide through by 75, and we are obviously going to do 5400 divided by 75 in the calculator. There's my calculator. So I'm going to do 5400 divided by 75, hit enter, I get 72. X equals 72. So 54 is 75% of that, what number there, that unknown was 72. That is one way that you can do many of the percent questions on this test. Obviously, I know some of you are looking at this and saying you would never have done it that way, that maybe you would have done just flat out proportion. In other words, you might have gone right to a step that looked like this, or maybe you did. Some people have that is of technique, which I have never really subscribed to. I will tell you that for a lot of the questions that appear on the SAT, a lot of more basic percent questions that appear on the SAT, this translation method, this translation chart that we just talked about is really, really efficient and really, really effective. Let's move on to example 2, where we will do a few more percent translations so that we can continue to see how this process would work. So since you do have some sense of how this works, you might want to pause the video and try these examples on your own before you watch me work through them. Example 2a, we have 15% of what number is equal to 35% of 120. I am going to circle that what number because that's what we're looking for. So 15%. Remember, 15% would translate to 15 divided by 100. That is 15 divided by 100 of, there's the of, what number, that's my unknown, that's what I need to know, is equal to, is just like an is, that would also translate to an equal sign. 35%, remember 35% means 35 over 100, 35 divided by 100 of 120. Remember that hint that we just mentioned, put everything over 1, might make it easier to see how to proceed, and indeed in this case I think it does. We've got 15x over 100 equals 35 times 120. I'm going to do in the calculator 35 times 120 equals 4200, so that is going to be 4200 over 100. Now we could cross multiply here. Our numbers are going to get a little bit big. We have a calculator, so it doesn't really matter. By the way, almost all percent questions that look like these will appear in section 4. You will occasionally see percents pop up in section 3, but the vast majority of percent questions will be in section 4. And obviously when you have a large calculation to do, you're almost certainly going to be in section 4 and therefore will be able to use the calculator. Instead of cross multiplying here, I am going to use a little bit of cleaning up here. I'm just going to multiply through by 100 and we'll be left with 15x equals 4200. I divide both sides by 15. Divide both sides by 15 to cancel the 15 there, and I get 4200 divided by 15, and I get that x equals 280. Let me see if that makes sense. 15% of 280 equals 35% of 120. Yeah, that would seem to make sense. We could actually check that here. Let's do 35 divided by 100 times, times 120. And then let's do 15 divided by 100 times 280. Let's make sure we get the same result, and we do. So x, the unknown here, is going to equal 280. In 2b, example 2b, we get 0.25 is what percent? What percent is x over 100 of is multiplication, 0.2. Again, I'm going to slap a 1 in the denominators for 0.2 on 0.25 and 0.2. Again, I'm just going to do what we've been doing. 0.25 over 1 equals 0.2x over 100. In this case, I am going to just cross multiply. I think that will be the simplest way to go. I get 0.2x equals 0.25 times 100. Obviously, you could just move the decimal over 2 times to be safe. I'm going to do it in the calculator. 0.25 times 100, enter, and I get 25. Obviously, now I am dividing by 0.2, divide by 0.2. Again, I'm going to go right to the calculator. I'm not going to try to do any of that in my head. And I get that x equals, where should I write this? Let me move this over a little bit. X equals 125. So it should be the case that 0.25 is 125% of 0.2. Let me check it. 125% of 0.2, and indeed I get 0.25. So I know that x is 125%. On example 2C, down at the bottom, I have a random sample of 600 cars, 5 of which have a manufacturing defect to the nearest 1/10 of a percent. Okay, so I am rounding here. What percent of the cars did not have, by the way, I should have circled the what there, or what percent. What percent not have manufacturing defect? So that's what I need to find here. What percent of the cars did not have a manufacturing defect? So translating what percent of the cars, that's 600, that's the number of cars. So what percent of the cars, 600, now did not have, would just translate to an equal sign. That's like an is or was or were. Did not have a manufacturing defect. Well, not have a manufacturing defect would be 595 cars, right? That's 600, take away the 5 that had the manufacturing defect, and we would have 595 cars. Again, slap all those integers over 1, and on the left we end up with 600x over 100 equals 595 over 1. Would it be easier here possibly to cancel some of those zeros? Yes, it probably would. So we get 6x equals 595. Again, we could have just cross multiplied there. That would have been perfectly fine. We're going to divide both sides by 6. So we get 595 divided by 6. And I get x equals 99 point. They wanted to the nearest 1/10. This 6 here tells me I want to round 99.16666 blah 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 to 99.2. So it should be the case that 99.2% of the cars did not have a manufacturing defect. Again, I could check that by doing 99.2 or even just using the 99.16% of 600, and my answer should be right around 595, and indeed it is. I'm getting a little bit above 595 because I rounded the percentage there to the nearest 1/10. So 99.2, obviously these two answers are percents. If example 2B and or 2C were grid-ins, you would obviously not be gridding in the percent symbol, as there is no way to grid a percent symbol. So there are a bunch of examples as to illustrating how we use the percent translation chart. At the top of the next page, we have to talk about percent increase, decrease. Percent increase, decrease is extremely common on this test. A lot of the percent questions that you encounter on the test will involve a percent increase or decrease. In other words, taking a number and increasing or decreasing that number by a certain percent. It is really important that you are familiar with all of the different ways that you can attack percent increase, decrease questions and all of the different variations as to how College Board can test percent increase and decrease. So there is a 2-step process, which most students are actually familiar with both the 2-step and the 1-step process. I think the 2-step process is a little bit more common among students, possibly because it's a little bit more intuitive. We will talk in a moment about the fact that you really do need to know how to do both methods, the 2-step and the 1-step. So for the 2-step, we've got the 2-step percent increase decrease process, and obviously it contains 2 steps. So here's what we're going to do. Using translation, we're going to perform this calculation, percent change of initial value. So here we have a percent change. Okay, so the percent change is, I'm going to write down percent change. The percent change is that we are decreasing by 35%. Really, it's just this 35 we're going to pay attention to. So we do percent change, which is 35%. I'm just translating 35% of the initial value, which is 80. So we're going to go right into our calculator, and we're going to do 35% of 80. And we're going to hit enter, and we get 28. So that 28 represents 35% of 80. Now, because this is a less than, we are going to take this 28 and we are going to subtract, this is step 2, we're going to subtract that 28, that result, from the initial value. The initial value, I'll actually jot that down here, was that 80. So we're simply going to do 80 minus 28, and we are going to get 80 minus 28 equals 52. So 35% less than 80 is equal to 52, because 35% of 80 is 28. So 35% less than 80 is the same as decreasing 80 by 28, which is 35% of 80, and we get our final value of 52. Let's do an example using the two-step percent increase decrease process. So in example 3, if you feel confident doing this on your own, go ahead and pause the video and do it. Example 3, a restaurant manager plans to increase the price of an entree by 6%. If the current price of the entree is $12.50, what will be the new price? So we need the new price. So again, what do? We find the percent change, right? This is increase 6%. So this is the percent change. And we said what we want to do is we want to first, as our first step, we want to find the 6% of $12.50. We'll want the percent change of the initial value. So we're going to do 6%, just doing some translating here, of 12.5 or $12.50. I'm going to put that in parentheses just so I don't mess up that multiplication dot with the decimal over here. So 6% of 12.5. In this case, just to remind you all that we, in the TI-84, we do have this n over d function. I'm going to actually use that here. That was alpha, and then the y equals, I'll show you one more time. I've done this in many other videos. Alpha, y equals, and then number 1, or just hit enter. So I'm going to do 6, and then in the denominator 100, and I'm going to be multiplying that by 12.5, and I'm going to hit enter, and I get 0.75, which obviously is in dollars. Because this was in dollars, this is in dollars. So now, step 2, remember what we do is we take the initial value and we add the result of step 1 to it. And of course, here we are going to get 13.25, but I'm going to do that in the calculator just to be safe. 12.5 and enter, and 13.25. So it appears that the new price, is that what they were asking? Yes, it is. The new price of this entree will be $13.25. I'm never going to this restaurant again. That's way too expensive. Just kidding. It's actually reasonably priced, depending upon what the entree is. That is the two-step method. The one-step method, which, again, a moment ago I said most students do find the two-step method a little bit more intuitive. The issue is that on the SAT, a lot of questions will be designed in such a way as to make the one-step method actually a little bit safer, a little bit quicker, a little bit more efficient. So it is important for students to know the one-step method. Let me shrink this down a little bit here. So the one-step percent increase decrease method, it involves converting a percent greater or less than to a percent of. So we're going to read through this, but it will be easier to see how this all works with an actual example. So what we're going to do is, when we're given a percent change, we're going to add or subtract that percent change. I'm going to go ahead and highlight this. We're going to add or subtract that percent change to or from 100. And then using translation, we are going to create a percent of calculation. We're going to create a percent of calculation. So what we're going to do is, if we're increasing a number n by a certain percentage p, increasing or decreasing n by a certain percentage p, what we are going to do is we are going to say that we are taking 100 plus p, that's what it says right here, adding the percent change, which is that p, to or from 100. So actually we should make this a plus or minus, depending upon whether we have an increase or a decrease. 100 plus p percent of the initial value of n, of the initial value. And obviously this is going to translate to 100 plus or minus p over 100 times n. 100 plus b percent, 100 plus b percent of the, why did I put a 10 there? That should have been an n. I have no idea why I wrote a 10 there. So 100 plus p over 100 of n. That is the translated percent of calculation. Let's actually hop back up to example 3 so that we can see how the one-step method would have worked here. You remember in the two-step method we found 6% of 12.5, which was 0.75, and then we took that 0.75 and added it to the starting value. That was the two-step method. In the one-step, maybe we'll add two-step over here just to differentiate from one step. In the one-step method, what we're going to do is we're going to recognize that increasing a value by 6%, is the same as taking 106% of that value. Again, we are translating an increase statement into an of statement, a percent increase statement into a percent of statement. So we're going to be taking 106% of that 1250. If we're just using the formula that we did down here, we just do 100 plus p is the percent change. In this case, that's 6%. And again, we're adding because this is an increase. So 100 plus 6 over 100 of the starting value, which we know was 12.5 in this case. And notice what all that equals. It equals 106 over 100, 100 plus 6, 106 over 100 times 12.5. And if you sort of translate this out of a mathematical expression, it says 106% of 12.5, 106% of 12.5. So 106% of 12.5 is exactly the same as increasing a certain value, in this case 12.5 by 6%. And indeed, if we go into the calculator, we will do, let's do that alpha f1 here, and we will do 106 over 100 times 12.5, and we should get 13.25, which is exactly what we got before, 13.25. So that is how the one-step method would work here. We are simply recognizing that increasing something by 6% would be the same as taking 106% of that number that we are increasing. Let's start trying a few other examples with the one-step method. Let's go down to example 4. If you feel confident doing this on your own, obviously feel free to work through example 4. If not, you'll just watch me work through example 4 right now. So in example 4, we have at the beginning of 2015, Francine had $3,600 in a checking account. By the end of 2015, the amount in the account had decreased by 4%. How much money was in the account at the end of 2015? So how much money end of 2015? So let's take a look at this. Here's the percent decrease, right? So this is a decrease of 4%. So that's the percent change. Here's the initial amount, initial, and percent change. I'm going to put a delta there. Delta means change. So again, converting into a percent of statement, we know that decreasing by 4% will look like 100 minus 4%. Okay, we're starting at 100% of the number. We're taking away 4% of the number of the initial value, which is 3,600. And mathematically, what does this look like? It looks like 96%. That 96 is 100 minus 4, 96% of 3,600. So decreasing 3,600 by 4% is exactly the same as taking 96% of 3,600. I'm just going to go ahead and type that right into the calculator. So what do I have here? I have 96 in the numerator, 100 in the denominator, and I am multiplying by 3,600. Easy peasy. I have 3,456 $3,456 in the account at the end of 2015. By the way, they could also just ask for the decrease itself, in which case you would just do 4% of 3,600. But in this case, since they wanted the final amount, the one-step method is probably the easiest way to go here. Trickier version here in example 5 at the bottom of the page. Again, if you're feeling fairly confident about all this, you can try example 5 on your own. If not, watch me work through it. In example 5, we have at the beginning of 2015, Francine had X dollars in a checking account. By the end of 2015, the amount in the account had decreased by 4%. If she had 3,600 in the account at the end of 2015, what's the value of X? So in this question, you can see that the numbers are sort of flipped. In the previous question, we had the starting amount, we decreased by 4%, and we need the final amount. In this question, we have the final amount that we arrived at by decreasing an initial amount by 4%. So again, here's the initial amount. Here is the percent change right there, that 4, and this is the final amount. So in terms of the one-step method here, it's not all that much different, except for the fact that what we are going to do is we are going to be decreasing X by 4%. So again, I'm just going to do almost exactly the same thing I did up here. That's going to be 100% of X minus 4% of X, which is going to equal obviously 96% of X. And 96% of X must equal that final amount, 3,600. So translating this into an equation, we know that 96% of X must equal 3,600, and there's my equation. I put all of these guys over 1. I get 96X over 100 on the left. On the right, I just get 3,600 over 1. Again, I could do a little bit of canceling or breaking down here, but actually I'm just going to go ahead and cross multiply. I'm going to do 96x equals 3,600, adding the 2 zeros for the 100 that I multiplied by. I divide both sides by 96, divide both sides by 96. 3, 6, 0. Well, how many zeros there? 1, 2, 3, 4. 1, 2, 3, 4. Don't want to make any careless mistakes. Divide by 96. That's not where I divide by 96. Divided by 96, and I get 3,750. So X equals 3,750. Does that make sense? I start with 3,750. I decrease by 4%. I get 3,600. Yeah, it seems to make sense. So I started with $3,750 in this account, lost 4%, ended up with 3,600. At the top of the next page, we are going to talk about an even further simplification of this one-step method. This simplification will become quite handy, quite useful, quite efficient on questions that involve multiple percent changes, where you're increasing by something and then maybe decreasing by something, or even decreasing and then decreasing again. Also on exponential function questions, which we will talk about in a different section of the manual. The simplification here will become really, really nice and useful on these two types of questions. So here's what we're going to do. We're going to look at how we might translate and simplify a statement like this. A is 30% greater than B. So A is 30% greater than B means we're going to take B and we're going to add to B 30% of itself, right? This is B plus 30% of B. And if we think about maybe common denominators or even decimals here, let's do it the common denominator way. This is 100 over 100b, right? This is 1b, and 1b is equal to 100 over 100b. So I'm just finding a common denominator. This 100 and this 100 now have denominator in common. So 30 over 100b, and what this becomes is A equals, sorry, let me get rid of that equals. This becomes A equals, well, 100 over 100 plus 30 over 100 is 130 over 100 times B, and this guy right here is 1.3. So A equals 1.3B. Again, I could have done this all with decimals from the beginning. I could have done A equals B plus 0.3B, and remember that's 1B plus 0.3B, and I get exactly the same thing. A equals 1.3B. This guy right here is what I refer to as a multiplier, and we have created that multiplier by converting a 30% increase in a number into 1.3 times that number. We're not doing anything different from what we just did. We're just presenting it in a slightly different manner. The way that we do this a little bit more formulaically, a little bit more efficiently, again, not that much different from what we did before. What we are going to do is to convert a p% increase or decrease into a multiplier, p% increase or decrease into a multiplier. We can sort of think about this the way we did before. We are taking that percent change and we are adding or subtracting that percent change to 100 and dividing by 100. But we should understand that this will also equal 1 plus p, 1 plus or minus, sorry, 1 plus or minus p over 100. We should be able to see that because 100 plus or minus p over 100 is exactly the same as 100 over 100 plus or minus p over 100. And 100 over 100 is just 1. That's kind of what we were doing up here. We were changing 1 into 100 over 100, and now we're just taking that 100 over 100 and we're converting it back to 1. So again, this will be your multiplier right here. 1 plus or minus the percent change over 100. Whatever that value is what you are multiplying by an initial number to get some final number. Let's do a bunch of examples where we simply create some multipliers out of a percent increase or decrease. If you feel confident with these, again, go ahead and try examples 7a through 7d. I'm going to work through them right now. Again, all we are doing is creating the multiplier. So if we decrease by 4.5%, what that means is we are going to be doing 1 minus 4.5 over 100. Okay, that is 1 minus, in this case we're decreasing, so minus, there's our percent change, divided by 100, and what this is going to equal, 1 minus 4.5 over 100 is going to equal 0.955, which is the multiplier. Now, some of you might be able to do this even more quickly, 0.955, by simply using this sort of a process here. Okay, either one of these is fine, where you say, well, if you decrease by something by 4.5, that means you will be taking 95.5% of the number, 95.5% of the number, right? 100 minus 4.5 is 95.5, and 95.5% expressed as a decimal, 95.5% expressed as a decimal, 95.5 divided by 100, again, is going to be 90.955. I don't really care how you arrive at the multiplier. If you have a way that works for you, the way that you think about it's really comfortable for you, that's perfectly fine. That's not a problem. Do it that way. I just gave you the formula here or here so that you would have some structured, consistent way to do this. So the sales tax of 6.7%, some of my students don't know that sales tax is actually added to a sales price. Some students think that it's subtracted or just get confused altogether. Sales tax is above and beyond a sales price. So this 6.7% is an increase. So what we're going to do again is we're going to do 1 plus 6.7%, 1 plus 6.7%, and of course that is going to equal, let's just do it in the calculator, 1 plus, I'm going to use the fraction here, 6.7 over 100, and we are going to get 1.067. So 1.067. So if we increase an amount, let's say a sales amount or a sales price by 6.7%, we could calculate what we are going to pay by multiplying the sales price by 1.067. This is our multiplier, 1.067. The next one I'm going to do in a, I think, slightly more efficient way. If something is on sale for 15% off, remember that that means that we are decreasing the price by 15%, which means we are going to end up at 85% of the price, right? If we have the price, which is 100% of itself, we take away 15%. On sale means we're taking away a certain percent. 15% off an amount means that we will have 85% of that amount, right? 100 minus 15 is 85. So 85% equals 0.85. That would be our multiplier, 0.85. Again, you can do this with the formula, just showing that there are other ways to think about this. If something is 148% greater than something else. This one's really tricky. A lot of students think the multiplier is 1.48, but if you actually follow this is why I'm giving you the formula so that you don't make careless mistakes. 1 plus, okay, greater than, so we're increasing by that 148%. 148 over 100, okay, that's 1 plus 148%, and what this is going to come out to is 1 plus 1.48. So your multiplier is actually going to be 2.48. You will be multiplying your initial value times 2.48 in order to increase by 148%. 2.48 is the multiplier. Multiple percent change questions down at the bottom of the page. These questions obviously are slightly more complex. These are some of the toughest percent increase decrease questions you will get. On a multiple percent change question, very frequently the multiplier method that we just discussed is going to be the easiest way to attack these. If you want to try example 8 on your own, pause the video and then come back and watch me work through it. If you want to just watch me work through it, that's fine too. In June, Jackson used 3.5 gigs of data on his mobile phone. The number of gigs he used in July was 65% less than the number of gigs he used in June, and the number of gigs he used in August was 150% greater than the number he used in July. Oh my goodness. If the number of gigabytes Jackson used in August can be represented by the expression x times y times 3.5, they want to know the value of xy. So again, mentioned a moment ago that the multiplier method is almost always the most reliable, most efficient method when you have multiple percent changes, which is what we have here. So let's take a look at this. I'm going to lay this out as follows. I'm going to write June, and in June there were 3.5 gigabytes used, 3.5 gigs. In July, that number, 3.5, decreased by 65%, right? There was the number in July is 65% less than the number in June. Well, remember, a decrease of 65% means that we're taking 35% of the number, right? I'll write this over here. 1 minus 65 over 100 equals, so my multiplier is going to be 1 minus, in this case, I'll just use parentheses, 65 divided by 100, just showing you a bunch of different ways we can make these calculations. So my multiplier is 0.35, and again, remember 0.35 is 35 over 100. That's what I said a moment ago. We are taking 35% of the original number. So what I'm going to do is I'm going to do 0.35, my multiplier, times 3.5, which was the number in June. So in July, Jackson will have used 35% of 3.5 gigabytes. Now in August, what we are going to do is we are going to increase the amount that was used in July. So this is the amount used in July, 0.35 times 3.5, and we are going to increase that by 150%. Well, again, multiplier there is going to be 1 plus 150 over 100. 1 plus 150 over 100 is going to be 1 plus 1.5. I could do that in the calculator. If you need to, that's fine. 1 plus 1.5, which equals 2.5. So now I'm taking the July amount and I'm multiplying by my multiplier, 2.5. Now, in order to figure out what x times y, the product xy has to be, which is what they are asking, I'm just going to rearrange this. I'm going to do 0.35, 2.5, and then the 3.5. And why am I rearranging it like that? Because that's how the expression is rearranged in the question. Well, they're just asking me what x times y is, right? X is going to be that 0.35, y is going to be the 2.5, although it could be reversed. It doesn't really matter. This is a product, and we could commute those terms. So I'm going to do 0.35 times 2.5, and I'm going to get 0.875. That 0.875 is the product of x and y. So 0.875 times 3.5 is the amount that Jackson would have used in August. Next page, we're going to do one more question. This one we are going to do with multipliers, but we're also going to do this question with tinning, with throwing in numbers. For those of you who have done one or more of the tin techniques, you should already be familiar with that, but for those of you that haven't, you should be able to follow what we're doing here. Anyway, the number y is, again, if you want to attack this on your own, pause the video and then come back and join us. The number y is 30% greater than the number x. The number z is 20% less than the number y, less than y. The number z is how many times, x. That's what they are asking. Z is how many times x. So with tinning, let's actually do the tin method first. What we are going to do is we are going to list our variables. We have an x, we have a y, and we have a z. So I'm just going to make a nice, neat, orderly variable list here. I'm going to throw in 100 for x. Why am I going to do that? Because it's going to make attacking this first phrase really simple. 30% greater than 100 is just 130. How do I know that? Because 30% of 100 is 30. 30% of 100 is 30. Any percent of 100 is just that percent. 5% of 100 is 5. 72.3% of 100 is 72.3. N% of 100 is N. Anytime we take a percent of 100, the result is just the actual percent, just the actual percent number. So increasing 100 by 30% to get y simply means that y is going to be 130. And now the number z is 20% less than y. How do I want to do that? Let's do it with the one-step method, where we say the number z is 20% less than y. That means that z is 80% of y. Z has to be 80% of y. So I'm going to go right here into the calculator, 80% of y, which is 130. So z has to be 104. 104. And now this part here at the very end, I can translate. Z is how many, I'm going to put an n there because that's like an unknown, how many times x, which is 100. And if I divide both sides by 100, I get n equals 104 over 100. 104 divided by 100 is, of course, 1.04. So that how many times is 1.04. That's how this question would work with the tin method. In fact, I'm going to write tin over here. Multiplier method, which again, some people might consider the multiplier method a little bit more efficient than the tin method. Either one is perfectly fine. Really just depends on which one you feel more comfortable with, which one you maybe have more time for, which one you think will be safer, more efficient, so on and so forth. The multiplier method here, we would do y is 30% greater than, let me get rid of that cross off, than x. So what does that mean? That means that y is 130% of x, right? Y is 30% greater than x. That means that y equals 130% of x. If we're using that multiplier formula, this is just going to be 1 plus 30%, right? There's the percent change. We do 1 plus that percent change over 100. And of course, 1 plus 30 over 100. 1 plus, let's do this, 30 over 100. Of course, that's going to be 1.3. So that means that y is 1.3 times x. That's what that first phrase tells us. The number z is 20% less than y. So I could deal with this y, but since at the end I have to relate z to x, I'm going to deal with this 1.3x. I mean, these two are equal to each other. So saying that the number z is 20% less than y is exactly the same as saying the number z is 20% less than 1.3x, because 1.3x is equal to y. So what I am now going to do is I'm going to decrease that 1.3x by 20%, and of course the multiplier there would be 0.8, because taking 20% away from something leaves you with 80% of that thing. Again, if we want to do multiplier here, this is 1 minus, we are decreasing 1 minus 20 over 100, 1 minus 20 divided by 100, and I get 0.8. So what I would do to get z is I would multiply 1.3x times 0.8, and that would give me, all of that would give me z. So that means that z equals, I'm going to rearrange all this so that I have 1.3 times 0.8 times x. Well, remember, the question was asking me z is how many times x. Z is how many times X. That how many is this 1.3 times 0.8 right there. 1.3 times 0.8 is 1.04, which is what we got before. That's how you would do this question with the multiplier. Repeating, we've got to move on to repeating equivalent percent changes. In other words, exponential functions. Exponential functions do show up probably once or twice per test. We will briefly introduce them here. And then, as I mentioned, there is an entire section elsewhere in this manual on exponential function. So what an exponential function is, what we mean by repeating equivalent percent changes is when we take a quantity and we repeatedly increase or decrease that quantity by the same percentage at regular intervals. Will be easier to see what we mean if we take a look at an example here. So let's suppose that in 2015 you were hired by a company given an initial salary of $60,000. And the company tells you that you are going to get a salary increase of 1.5% each year after 2015. So each year you're going to get a 1.5% salary increase. The multiple here would be 1.015. We're just doing 1 plus that 1.5 increase divided by 100. 1 plus 1.5 over 100 is 1.015. So this will be the multiplier by which we will multiply our salary to get the subsequent year's salary. Going to be, again, easier to see if we look at this little table down here. So in 2015, 0 years after 2015, 0 years after 2015 means you're in 2015, your salary is just going to be $60,000, and you can see that that's $60,000 times 1.015, your multiplier to the 0. Remember that 1.015 to the 0 just equals 1, so this is 60,000 times 1, which is just, again, 60,000. Now, 1 year after 2015, that's in 2016, you will find your salary for that 1 year, salary 1 year after 2015. So this is, again, this is the expression we're using to represent your salary in 2016. 1 year after 2015 would be your salary in the 0 year, which was 2015, which was that 60,000, times 1.015. Again, we would just take 60,000, we would multiply 60,000 by our multiplier 1.015, and we would get our new salary. So simplified, we could say that your salary in 2016 would be $60,000, your initial salary, times 1 multiplier, times 1 multiplier, 1.015 to the 1. Now, we're not going to actually calculate this out because the actual value is irrelevant here. We want to look at the structure of what's going on here and discover how to structure any similar type of scenario. Now, in 2017, which is 2 years after 2015, so this is your salary 2 years after 2015, so this would be the expression we're using to represent your salary in 2017. What you would do is you would take your salary 1 year after 2015, in other words, your salary in 2016, and you would multiply that salary by 1.015. Again, that's what we said. We're just going to keep multiplying a certain quantity by the same percent increase or decrease, in this case, a multiplier, over and over and over again. So if you look at what's going on over here, you have got your 2016 salary right here, and we're just bringing that down here. There's your 2016 salary, and we're multiplying that 2016 salary by another 1.015 because we are increasing once again by 1.5%. So we should be able to see that in 2017, to get our salary in that year, we would take our initial salary and we would multiply it once by 1.015 to get the 2016 salary, and then we would multiply again by 1.015 to get the 2017 salary, which means that 2 years after 2015, we can find our salary by taking our initial salary and multiplying by 2 1.015s. And then, of course, 3 years after, we would take our initial salary, multiply by 1 multiplier, the multiplier again, and then a third multiplier. So we would be taking our initial salary and multiplying by that multiplier 3 times. We should, probably the most important thing here is to be able to see that the number of years after 2015 is the same as the exponent on the multiplier. Okay, for every year we go past 2015, we multiply by one more 1.015 multiplier. So we could write a generic equation here and say that t years after 2015, our salary t years after 2015 will be 60,000. Again, that's the initial salary, times t multipliers. Okay, and when I say t multipliers, obviously that t is an exponent because whatever t is the number of multipliers we were multiplying by 60,000. So 3 years after, 3 multipliers, 4 years after, before, 5 years after, be 5, and so on and so forth. This is how exponential functions work. Exponential functions work by multiplying an initial value by some multiplier. In this case, that multiplier was found by a percent increase, and we simply, every time another year passes, we multiply by another multiplier. We're going to do example 10. If you're comfortable with exponential functions and you understood everything we just did, maybe you were solid on exponential functions before, you should be able to do number 10 on your own. Go ahead and try it out if you would like. If not, watch me work through it. So here we have Jackson again using 3.5 gigabytes in 2014, June of 2014. For each of the next 6 months after June, the number of gigabytes Jackson used was 2.1% less than the number of gigs he had used the previous month. Write an expression for the number of gigabytes Jackson used in the nth month after blah, blah, blah. So expression, number of gigabytes, nth month after June 2014. Okay, so our starting value is there. That's the 3.5. Our multiplier, remember we said, as in the previous example, our initial value is going to be out here. So I'm just putting my initial value there. Now we've got to figure out the multiplier. And the multiplier here is going to be 1 minus, this is a less than, 1 minus 2.1 over 100. Again, if you're able to do this quickly in your head without using that formula, I'm perfectly fine with that. But we're going to do 1 minus alpha F1, enter, and 2.1 over 100. So we're going to get 0.979. That's our multiplier, 0.979. And again, as I said, if you're able to recognize that 100 minus 2.1 is 97.9, so 97.9%. That's perfectly fine as well. There's multiple ways to come up with your multiplier. So that's our multiplier. So for instance, 1 month after June of 2014, we would be at 0.979 times 3.5. 2 months after, we would have to multiply by another 0.979. 3 months after, another 0.979. So 1 month, and then 2 months, and then 3 months. So it appears that our expression could be 3.5 times 0.979 to the n for nth month, right? 1 month, 1. 2 months, 2 multipliers. 3 months, 3 multipliers. N months, n multipliers. So our expression could be 3.5 times 0.979 to the n. However many months past June of 2014 is the number of times we will multiply 3.5 times 0.979 to decrease an additional time by 2.1%. Hopefully that makes sense. Again, if it didn't, you will get more experience with exponential functions once we hit the exponential functions section. Don't worry too much about exponential functions at this point. You should just have some sense that this is how they work. At the top of the next page, we need to talk about calculating a percent change, and then we will be finished. Calculating a percent change, what we mean here is if you're given the starting value and you're given the final value, you're given an initial and a final, and you need to calculate the percent change. You will recall that in all the previous examples, we were given the percent change and we had to go from an initial value to a final value using that percent change. But if the initial and the final value are given and you need to find the percent change, you just got to know this formula. If you know the percent change formula, you're going to be fine on these questions. If you don't, there is a possibility you're going to be lost and you're going to miss some easy points. The percent change formula is very simple. It is final minus initial And I'm going to rewrite that because that's ugly. Final minus initial. I'm going to put that in absolute value. You don't really need to worry about positives and negatives on these questions. And then what we do is we divide by the initial. What am I doing with my spelling today? Initial. And finally, we multiply by 100. I'm going to put the multiply by 100 over here. So final minus initial over initial times 100. Another way that we could write this, maybe even a little bit more simply, is the change over, so I'm going to draw a bar here, change over initial times 100. Change over initial times 100. That might be the easier way to remember this formula. And by the way, if you have done, some of my students bring up that they've seen this formula before, maybe in chemistry where they're doing percent yields or something like that. So most likely you've seen this formula, this expression in some form or another at various points in your schooling. But again, just memorize change over initial times 100 or final minus initial over initial times 100. Example 11, calculating a percent change. So we've got, again, probably best to pause the video and try this one on your own and then come back and join me. Last month, a home used an average of 124 gallons of water per day. This month, the same home used an average of 118 gallons of water per day, rounded to the nearest tenth by what percent number of gallons decrease? So we need the percent decrease from 124 to 118. So again, what do? We do the change over the initial times 100. So I am going to do this 118 minus 124, that's the final, initial. Remember, we can keep this in absolute value, all over the initial, which is 124 times 100. Now, there is a way, if you do have the TI-84, that you can punch this in the calculator exactly as it appears on the page so you don't mess anything up. We're going to do alpha, F1, enter, and then most TI-84s, newer ones at least, and by newer I mean within the last 20 years, we're going to do alpha and F2 and number 1. Even if you have a slightly older TI calculator, not the CE, you still should see that absolute value function in the F2 menu. I'm going to do that one more time. So again, I'm going to hit alpha and then Y equals, which will bring up my F1 menu, which has all my fraction options. So I'm going to hit number 1, or I could just hit enter. So now I have my fraction. Then I hit alpha and I hit the window button to bring up my F2 menu. And the very first item in my F2 menu is absolute value. You can also access your absolute value in your math menu. If you hit math and then you scroll to number, the very first thing under number will be absolute value. So you don't have to get absolute value in the F2 menu, but it is a convenient way to get to it. So now what I'm going to do 118 minus 124, 124 over 124. Do I want to just throw in the times 100? Yes, I do. Times 100, and I hit enter. So my percent change is going to be 4.8387. They do tell me to round to the nearest tenth. Rounding to the nearest tenth, that 8 is the tenths digit. There is a 3 here, so I just stay at 4.8. So I know that the percent decrease from 124 to 118 is 4.8%. I have decreased my water usage by 4.8%. Yay me, yay environment, yay percentages. That is it for percentages. Obviously, there are a bunch of things to memorize in this section. Obviously, first to understand them and then to memorize them. You've got to know how to translate percent questions. You've got to know how to create multipliers. You should both know the 1 and 2 step method for percent increase decrease questions. You should know how to create multipliers. You should have some sense of what exponential functions are, especially when they obviously involve percentages. And then of course you need to memorize the change over initial times 100 as your percent increase decrease formula.